In this tutorial, we are going to see how we can use machine learning for object classification. First of all, we will load our data. We will see how the data should be arranged for classification application, and we will define our training and validation data set. And then we will look into some examples of training and validation data. Just we will plot and see what the data really looks like. Then we will define a model, a machine learning model that will enable classification of an image, uh, and then followed by the model, we will use compile, and we will use the standard library from TensorFlow to compile the model, and that includes optimization and minimization of the loss function. And then what we will also do is that we will log the training and validation log accuracy in our computer locally, and then train the model. We would visualize the loss in the tensorboard while the model is being trained. And then after we have trained the model, then we would want to save the model in local drive for inference purpose. This is important because whenever we want to train the model only once and then use the same model for inference, so we would want to save the model and then use it for inference, unlike that we would want to train it every time. So we do not want to do that. We want to train our model, save the model, and then use the model for inference or for detection or for classification. That's why this part is important. And then after we have saved the model, we will reload the model, and then check for inference, and we will end with the summary, and we will look into the model parameters. So how many of the model parameters are trainable and how many are non-trainable, and then use and then make an inference from the model that we just trained, and then finally validate our model using confusion matrix. This is our folder, the main folder. We have this object classification, and we have the folder here. The folder consists of 5 classes or 5 types of flower, and we populate the each folder with the particular flowers of that type. For example, if we want to classify 5 flowers of different types, we would create 5 folders and put the flower of that particular type in that folder. For example, if we have daisy flowers to be classified, then we capture the image of daisy and put it in this folder. So, and then similarly, if we have dandelion, we capture the image and then put it in this. So we have almost 900 dandelion here, and similarly for the roses. So the key concept here is that make a folder for each type of object that you would want to classify, and put it in the folder. And then I have created this model, saved model, that where we want to save our model as explained earlier, and this is our file, and we would want to open this. So what I can do is that I can open this folder with and then we have this our folder here. So first of all, we would want to load our dependencies. I can just minimize this now here, and this is the file that we would want to run, and I will explain this in a while. Yes, this is the file that contains all the code for object classification. First of all, we would want to import all the libraries, and what I prefer is to do to run run each cell rather than running the all file, so that we know what is happening. And before that, make sure that you have your virtual environment that we installed, that we prepared in the first lecture. So activate the virtual environment, and I have already activated here. And then we would want to run this, so we can go to run in interactive video. So it would be connecting to the MAS 512 kernel. Yes, so we have this file, and then this is the directory where I have the folders. I have my folders here in this directory. So just to replace this line with the folder where you have your image stored, and you define your, and we define our image size here, and then we initialize our batch size, that is the number of images that the model is gonna take for during its training. And this is how you these are the built-in functions from TensorFlow, and this is how you create your training data set. And then there are other important parameters here that I have labeled it, that we do not need for this particular example, but feel free to explore about them. So we have our batch size, and what important is batch size, image size, and then the seed. That means when this is to randomize the image, but it randomizes the image in the same pattern every time. And and we would want to have this validation split, that is 20 0.2. that means 20% of this training data set is kept as validation, and 80% is used for training. And then we have this is our training data set. And similarly for the validation data set, the same thing, we just repeat it and just make it here validation. So this is how you have your training and validation data set. And then just we can just run this. Yeah, so we have almost 3670 files in the 5 classes, and we are using 80% of them for training, and almost 735 for validation, and there are 5 classes. So this is the summary of our data, and our data is here. So we have 5 classes, and each of them consists of images. Yeah, after we have done that, we would want to see what are the images in our data set, and print the shape. So we have the image size is 180 by 180 by 3, and 16 is the batch size. And then we would want to plot it. So let me make this bigger. Yeah, so these are some examples, random examples of the training data set. And this is our model. So while training, what we want to do is that first declare the number of classes we have. So number of classes is 5, and then as we saw in the class, we have the sequential. And then we would want to the first layer is the scaling. That means different images might be of different intensity, so we would want to convert them into 0 to 1, and that is why this is rescaling. So we always want to rescale them so that all the pixels are in the same range, otherwise there might be some optimization problem or training explosion. And then we have this convolution layer. So this is the number of filters, and this is the size of the filter, and then we are using this activation ReLU, and then the max pooling, as we saw in the class. So we have this experimental scaling first, and then we use a series of convolution layer followed by max pooling, and the same. So as we go deeper, so we would increase the number of filters, and then for each layer we keep on learning the features. So here we have 4 filters, and then 8, 16, 32. And then after we have done this convolution, so we would want to flatten them. That means just stretch them into one dimensional, and then use the dense layer with activation ReLU. And this is regularization. So we haven't seen this in the class, but what this does is that it stops you from overfitting or underfitting. So you might not want to use it, but it's good to know about regularizers, so that you can explore its functionalities. And the most important thing here is that for classification, the last layer doesn't matter all the previous layer what you use, but the last layer should always be number of classes. So if a number of classes is 5, the last layer should contain of 5 neurons only, and then activation should be softmax for multi-class labeling. So if you use a ReLU here, that would be a problem, because softmax, what softmax does is that it gives you the probability of the object falling in each of the classes. So once we have defined our model, and so only different thing here for the detection problem is that for the classification, the last layer should always be dense, and the number of neurons should be equal to number of classes, and then the activation should be softmax, because it gives you the probability of the object falling in this particular class. And then we compile the model that we saw in our object detection in the previous tutorial. So it is almost the same thing, except that we have our I have defined here a stochastic gradient descent with learning rate 0.001, and then the loss here, unlike in the regression problem where we had the loss of root mean square error, in the detection we had something else, and then but here we use sparse categorical cross entropy. So this loss just determines that that if what level have you predicted it, and what is the ground truth, and calculates the cross entropy bit of that. So this is a type of loss that we use for classification, and then we want to find the accuracy. So the same thing, here we have our log directory where we want to log our data. So basically you will have your data logged here. So we will have our data logged here. So right now there is nothing, so we don't have any data logged here. So we have our data logged here in this path, and then what we are logging is we log our data, and then we log each epoch. So maybe you want to have batch, but I prefer to have epoch. So we update our data each epoch. These are the same thing from the regression or from the object detection module, and then we validate. So we fit our model on with training data and validation data, and validate it on our validation data, and we train it for 100 epochs. So all these things are the same with the object detection. If you haven't seen them, I would ask you to go and look into the object detection lab tutorial. I will leave the link in the description. So let's run it for 100 epoch, so that we have trained the model for 100 epoch. So yeah, so here you have integrated tensorboard already integrated with VS Code, and I would say yes, so that you could look into the VS Code current directory. So the tensorboard is starting. So good thing with VS Code is now you have integrated tensorboard to visualize your loss. So in other IDE you have to start it manually, but here VS Code does that for you. And if this doesn't show up, I would suggest you to hit Ctrl+Shift+P, and then you would get this option, launch tensorboard. But it should be done automatically. If not, hit here. So one is already running, so I think we have to be patient. But in the meantime, we can have a look into here so this is what I meant. So all the logs will be logged in this folder. So earlier we didn't have this folder, but now we have where our training and validation data would be logged in. So while it's training, so there is some errors, so maybe then we can hit Ctrl+Shift+P and launch tensorboard current directory. So while it's training, I will be back. I'll pause the video, and while it's training, I'll be back. So I have my tensorboard launched here. So just a quick note on the tensorboard, what we are interested in: epoch loss. So this is how the epoch, and then we have our epoch accuracy. So we would want to see this. So I can just minimize this now. So you can just play around what you think is best for you. So for me, I would, yeah, so I would stick to this one. So you could even download data and then plot and keep its video. So it's always good to have this option enabled, epoch accuracy, and then you fit data. So while it's training, I would pause my video, and then I'll be back when after the training is done. Finally, we have trained our model, and then we have the tensorboard here. So let's update it. Yeah, and it has been trained for 100 epoch, and it looks like there is a slight overfitting because our the black curve is for training accuracy, and the blue one is the validation. So validation is performing a bit worse than the training. And then let's look into the loss curve. Yeah, I mean the loss for the training is very steep, and then with the validation it starts to get diverging, but it's not that bad either. So the loss curves and the accuracy curves looks okay, but overall we will have to look into our confusion matrix and validate. Yeah, so once we have trained our model, so we would want to plot the history. Yeah, and this is what we get it here. This is exactly the same thing that we got from the tensorboard, our validation and validation accuracy and training accuracy. So there is, yeah, the model might not be that good, but we will see it. So once we have done this, so now we have our validation and training loss and accuracy both. So what we can do, what we will do now is to save the model. So you save your model using model.save. So you use this model.save, and then you give it a path where you want to save the model, and we are saving it as H5 format. So this is what we discussed in the beginning, that we would want to save this model and make inference only using the model, so that we don't have to keep on training every time. So once we have this, then our model is saved here in this folder. So we have this model saved, and then the naming convention is as follows. So we have year, month, date, time. So it's 12, almost 1 in the morning. Yeah, and then we can just load our model and see our model parameter, just to check that okay, our model has been saved correctly. So you load the model using this command. So load model, and this is the summary of our model. So it has almost 75,000 parameters, and all of them are trainable. And then we can do some inference here. So let's see our inference. So here what we are doing here is that we are loading an image. I'm giving it a path. So we have flower photos, tulips. So we are basically, what we are doing here is that we are giving it tulip here, and we are giving it this this image as an testing. So let's see how our model behaves to this image. So we pass this image, and then we try to make a prediction on this image. So it is tulip and then it predicts tulip. Yeah, so we see here, so this is what I said about when we talk about softmax here in our model where we had this softmax. So this is what softmax does. So softmax, we have 5 layers, 5 neurons on the last layer, and softmax gives you the probability that this is class 0, class 1, 2, 3, 4. So basically the first element of this prediction, yeah, when we say this predict class, so the first element gives you the class 0, so that means class daisy. The second element would mean dandelion, and third element would mean roses, and so forth. So we see here, so 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4. Yeah, so fourth element had the highest, so it predicts as a tulip. So this is what softmax does. So each of these is a probability. So it tells that there is 10% chance that this is of class 0, that means it's daisy, and again 10% chance that it is dandelion, and again the third class was rose, so it is 22% chance that this flower is rose, and finally it is almost 68% chance that this is tulip, and then you just read the maximum. So we use argmax to find the predicted one. So now we did for one, so let's do it for all the other classes. So what we do is that we do this for all the other classes and see what we have our confusion matrix. So what confusion matrix does is that it takes your true value and then the predicted value, and then it plots them as a matrix to see the performance of our model. So this is how you find your predicted. So you find the maximum, the index where the element has the maximum value. So I find this one. So model.predict. So you use this model.predict. You could also use loaded model. So it's basically the same thing. So loaded model.predict, or you can use the model.predict. So this model is our model here. This is our model, and loaded model is the one that we have saved it and then loaded again. So both basically are the same thing. So I'm just giving you example. That means this loaded.model, this prediction of this part is done by saving the model and then loading the model, but here we are just doing on the model.predict. So let's see how our confusion matrix is. Yeah, so let's do an interpretation of our confusion matrix. So confusion matrix takes two input. So first the true value, that means what exactly is the label of the image, and the predicted, what your model predicted. So if you look into this, so your first element is 1, so that means when your label is 1, your prediction is 4. So that means while your label is 1, that means while your label was daisy, the model was predicting tulip for the first validation, and then the same thing. So for example, the last element here is 2, so your ground truth was class 2, and then your prediction was also class 2. So class 2, and then we can just look into here, y true. So y true and y predict. Yeah, so 1, 2, so that means while your first label is 1, so that means dandelion. Our prediction was 4, tulip. So, and what this confusion matrix does is that it gives the probability that how many of them were detected truly and how much them were detected false. So yeah, so and then if you look into the interpretation of this confusion matrix, it is an KPI giving you the overall performance of your model. So what this really means is that 9%, when my the daisy 9% of the time the model classifies daisy correctly, and rest of the time it classifies them as dandelion, roses, sunflowers, tulip. So this is not a good model. So in fact it should be 1 everywhere in the diagonal. So 1 means 100%. This is plotted as a percentage. So if you just want to find the number here, cm, so you can just replace this by cm and it will give you the number. So it's 11. So basically you can just look into the, instead of number, I prefer to look into the percentage. So it means that 9% is 9% of the total image that was daisy was classified true, and then the rest was 22% is classified as dandelion, 9% as roses, 35% as sunflower, and so forth. And if we had basically we want 1 in the diagonal and rest should be 0. So this is an average model, and then but this is how you get to classify an object in the using machine learning. And similarly, so dandelion 28, so 28% of the time dandelion was truly corrected, truly identified, and but 12% of the time dandelion was identified as daisy, 14% of the time as roses, 33% sunflowers, and 13% tulips. So we see we have got a mixed performance here. Basically this model is not good. Ideally it should be close to 1 and rest of them should be 0. So but we have to play with this model and then come up optimize it. So we might want to change add regularizer, but the model is not overfitting or underfitting. We would also want to train it for maybe higher epoch, for example. So instead of having we could train it with 1000 or 5000 epoch, and then we would make it our model deeper. So and then we would also want to increase the number of filters so that we can learn more features. So there are many ways that we can improve our model, but this gives you an overall end-to-end definition of the model, how you save it and how you do the inference. And then the key takeaway is the confusion matrix that validates your model, and on the diagonal side it should be 1 and rest should be close to 0. So this is where we can end our classification. And similarly, if you want to classify something of different, for example, if you want to classify your image that's healthy tissue or malignant tissue for cancer detection, so you could just make 2 folders here, malignant and non-malignant, and then put the images for the malignant here and non-malignant in this folder, and then everything remains the same. And before I end, I would ask a quick note on the standard model that has been already been implemented in TensorFlow, and it is the state of the art. For example, MobileNet, Inception, ImageNet, DenseNet. So these are the standard model that has been tested and validated in the state of the art. So instead of writing your own model, what we normally do is that instantiate this class, for example, RAS50, RASnet 50. So if you just write 1 line of code here, RASnet 50. So the RASnet 50 is an convolution neural network that has been that's the current state, that's the state of the art, and it's validated. So you could just implement it using one line of code. And there are similarly, there are if you go to the detection model zoom, I will leave the link in the description, that all these things has been already implemented. So instead of writing your model from the scratch, it's wise that we implement we just instantiate these things and make changes over this. And similarly, we have this model garden, and I will leave the link of this for future or for curious students to have a look into that. So that ends our classification. I will leave the link in the description, and then if there is something that's not clear, please let me know in the comments. Well, thank you.